It's a pleasure to be here. Dr. Kavraki, Dr. Hu, thank you so much for inviting me, and good to see so many faces here. So I have a story here about digital twin, and I'm going to talk about different projects. I hope I can bring the concept home at the end. The shuttle program started in 1981, and it ended in 2011. The shuttle, when it enters the orbit and it starts descending, it has only one shot, right? It doesn't have an engine. It has a small engine. And then it lands in Florida. There is a whole setup around this that supports the astronauts and the descent of the shuttle with all the computation and all the experts in the background. I'm going to touch on this concept again in a few minutes when we talk about the cardiovascular health and digital twin. But what I'm really referring to here is what is so-called actionable information. The information that comes from this is controlling every single second of the movement of the shuttle as it lands safely in Florida or Johnson Space Center, either of So I'm going to motivate that in the context of blood pressure. When we started working on this project, which has a very interesting story, by the way, I'm happy to share that during the break. The question was why blood pressure is so important for us. And when you look at the human physiology, so you have heart at the center. The heart has a heartbeat. And then we have so much blood that would leave the heart with every stroke. Combination of these two would give us what is so-called cardiac output, how much blood leaves the heart. Now, the interesting part is when the blood leaves the heart, it doesn't go into solid pipes. It goes to our arteries, which have compliance. So as the blood flows into the arteries, they expand and they squeeze. The expansion and the squeezing of the artery is really the root cause of blood pressure. If they become stiff, the heart has to work harder because it needs to send more blood to the cells. And then over time, the heart becomes a stronger muscle. And you end up with a sustained hypertension. But the point here is that the blood pressure really is a reflective of the behavior of the heart and our peripheral resistance. This is really important. You might have heard about the term stress kills, right? We don't know exactly how. We can measure the blood pressure when we are stressed out, but it has to do with the stiffness of artery. And over time, that leads to, again, other complications. So blood pressure is a time series signal, just like any other time series. You have the minimum blood pressure, which is diastolic, systolic, and there is a waveform associated with it. If you're lucky, we capture this maybe once or twice a day. But there is a whole value in this waveform. There is so much value for us to be able to capture this continuously, at least during the nighttime. So today, I'm going to talk a little bit about the data, a little bit about the AI, and how physiological models can bring all of these together and really take us in the direction of digital twin. So we have been building sensors. These are bioimpedance sensors that can measure impedance. We measure the blood volumetric changes. The reason we use bioimpedance quite a bit is because the bioimpedance can go deep into the tissue. Has a couple of advantages. We need to go into the arteries to capture the measurement. If somebody is has a higher weight, there is a thicker layer of fat on the skin that would prevent other modalities to work as well, but bioimpedance can go deep into the tissue. And then bioimpedance is not sensitive to the skin tones. That's also another important advantage. There are different versions that are supported by different projects. This is a fully sort of our Rolls-Royce benchtop. This is a wearable one. This is the latest one, Dean Osman. He actually comes here to NMED quite often. He's the inventor of this, and it can measure the blood pressure from the finger. And then we have also shown how the skin tone would impact the measurements. So data plays an important role in any field, including development of AI. How do we measure the blood pressure? So you can always ask people to record the blood pressure one measure per day, but that's not enough to train the machine learning algorithm. So we often use this device, which is called FenaPress. It gives you beat-to-beat blood pressure. It's about $50,000. And then we introduce maneuvers. We ask individuals to do hand gripper tests, put their hand or feet in a cold presser. We ask them to exercise. They go through the whole process. We take all the measurements, and you generate a range of blood pressure values. And this is really how the setup looks like. So I'm going to talk a little bit about the estimation, and I would go into the digital twin. So here I have a robot on the screen. This robot is moving around, has a bunch of sensors. that can measure its distance with the obstacles. The objective is to use those sensors and figure out where that robot is. Okay? So when it starts, any location could be the location of the robot. And then you take the measurements from the sensors, and then over time, you end up converging to where the robot could be. This notion is called particle filters. We have been using that quite a bit for navigation, in robotics, in vision, and so on. So now, what does it have to do with the digital health and cardiovascular health? Very similar to this example, we have a lot of sensors around us. Some sensors may work well, some sensors may not work as well. There are different modalities. And then also, oftentimes, when we are trying to measure something like heart rate or blood pressure, we have only one blood pressure. But if we have too much noise, it's okay to assume that we have two different values or multiple values. We track multiple hypotheses. A lot of times in digital health, we're exactly looking at this kind of map. We're trying to figure out where we are. So now I'm going to give you an example here in the context of two things so that the concept would come through. Is that I can have a signal that is electrocardiogram. I'm trying to measure the heart rate. I can find the peak-to-peak distance between every two peaks here. You have two windows that are moving each other exhaustively. You measure all of them. The order is still order of 1 because the size of the windows are constant. So that's one of your observation mechanisms where we try to measure the heart rate. You can have optical sensors like what I have on my watch, and then you take the spectrogram and you try to measure where the signal is. So that's another observation mechanism. Then I can have an accelerometer. I know accelerometer doesn't give me the heart rate, but it can give me the noise. If I happen to get a signal from the accelerometer, I can go back and question that. So I do the same thing, but I would take sort of the reverse of the observation. I don't need to go into the details of it. This is the idea of particle filter. You take the particles that are uniformly distributed between the minimum and maximum heart rate value with the same weight. You take the observation mechanisms, fuse them, normalize them. You do resampling to eliminate the particles that you don't need. And then at the end, you end up detecting the heart rate. We use the notion of clicks because the heart rate would slightly change. And then you measure the posterior probability, and then you can figure out how much contribution you have from the sensor. So the math is not really important, and really the result is not important. But what is more important is we have the ability to actually track multiple hypotheses. This technique would also give us a really good understanding of how much noise we have in our signal. It's important when we talk about actionable information. If you get a distribution that is a new unimodal, really clean, it tells you that you have a good signal. If you get a bimodal or multimodal distribution like this, it means that you have more noise in your signal. Again, it's not important how good the results are. They are very good, but really what is more important is you can track multiple hypotheses. You can figure out how much contribution you have from each sensor. And then the particle filter, oftentimes for wearables, also gives us a really nice trade-off to change your computational load versus accuracy. If you have less power, just reduce the number of particles. If you cannot tolerate that, you have to increase the number of particles. So this was the work that actually Nathan did as a part of his PhD. And then Jonathan Martinez, who just graduated with flying colors just a few months ago, he took the concept and he tried to apply this to the blood pressure. So this is a signal that we get from bioimpedance. And then I can look at one heartbeat. I use machine learning AI algorithms to extract my systolic and diastolic blood pressure. Okay, so that's great, and we have done it many times. But then the alternative approach is instead of looking at only one heartbeat, I look at two heartbeats, and I measure the differential blood pressure. The advantage is twofold. One is when you're looking at differences, you have to worry less about calibration. And then the second approach, which is more important, is you're going to have a lot of those differences. You have a lot of redundancy. Now you can bring it into the particle filter framework and do a good job with the blood pressure. So I won't go into the details of it, same concept. But so when you take the measurement, the differences, you have the difference between this point and this point, time t1 and t2, and there is another time in between them. The blood pressure change from t1 to t2 should be the same as T1 plus T3 and then T3 to T2, right? Because you have this additive property. So you can use that to check how good your particles are and change their property. You could also measure blood pressure in different ways. Diastolic is the minimum. Systolic is the maximum. The difference between systolic and diastolic is a pulse pressure. So you can measure all three of them and check if they agree with each other. And if they don't, you reduce the weight of the particles. So this approach turns out to actually work really well. Again, it outperforms all the other techniques, but really the most important part is that it can work with that multi-hypothesis framework. And what is important, and I think, and I like to sort of encourage our physician scientists to consider this also, is that if I happen to measure blood pressure once a day, I have to have some notion of error, right? And the error could be root mean square error. How much difference you have compared to a gold standard blood pressure. But if I happen to measure blood pressure 1,500 times a day, does it matter if one measurement has a high error? Maybe the correlation becomes more important, right? You're trying to identify nocturnal blood pressure measurements for non-dippers, right? The distribution gives us more insight. So, but the distribution and really the correlations are actually fairly fantastic. So I'm going to talk a little bit about digital twin, and then I will close the talk. So, we talk a little bit about the data, and the data would drive the AI development. In image processing and vision, we have looked at a lot of these algorithms, and there is really no shortage of these stop signs or different kind of signs that your autonomous driving vehicle should be able to detect it. But what's the equivalent of that in health? How many stroke incidents can you generate? Probably none. If you know the person is going to have a stroke, you have to take an action on it, right? So this motivates really the value of the data and how hard it is to generate data that corresponds to the disease state. The data is personalized for digital twin, and then you also consider the noise. And in many cases, the disease state may not be available. So this brings the notion of model, which is sort of the base of digital twin. If I don't have enough data, I have to have some model that would help me to use my limited amount of data and extract other things. Is that fair? Okay. There is no shortage of that. These models have been around since 80s. But the problem is this model, first of all, has a lot of hidden parameters that it's really hard to customize. And the model only becomes actionable when it's for me. I can't take Khan's model and apply it to my health, right? So that's really one of the challenges when it comes to the personalization. The burden associated with comprehensive measurements and the wearables or time series do not give us what we need to get. I really like this definition by Karen Wilcox. She's at Odin Institute. She's the director of Odin Institute. A digital twin is a computational model that evolves over time. It persistently represents the physical system. And there is a two-way flow of information from the digital twin to the physical twin. This is important. If I take a model, if I don't update it, that's not a digital twin. It has to be continuously updated to our health. And then also, I need to be able to, you look at my digital twin and understand the trajectory of my physical model. Similar to what we talked about when we talked about the shuttle, right? NASA knows where the shuttle is going. We really need to be thinking about it in the context of all our 11 organs. We have 11 organs. We need to be thinking about it in the context of creating digital twin at the level of cell, tissue, organs, and organ systems, and the full body. Those are some of the challenging problems. Digital twin, the base is model. How do you personalize model? Well, using sensor. And then AI is going to actually act as a proxy between these two, and oftentimes it can actually act as a proxy for the models too. So here is an example. I have the human, and I have the data associated with human. First of all, I have the genomic data. I have all the phenotyping data. I have EHR, EMR data. I have the wearable data. Find one machine learning AI algorithm that can combine all of those. It's impossible, right? Instead, we have to use the model to bring all of these together. So you use the data to construct the models. The models are physiological models that you try to refine. But then sometimes you cannot build a physiological model. I'm going to talk about it in a second. You can instead use the AI to act as a surrogate for that. And in other instances, you want to build an AI, you let the model drive the AI development. We really need this at the level of cell, tissue, organs, organ systems, and digital human. And then we extract information. We use this, again, two-way flow of information between these two. So I don't have time, but I would like to ask you to read a little bit about the bio of Dr. Tinsley Oden. He passed away on August 28th, I think, sort of tragically about a few weeks before the 50th anniversary of Oden Institute. In the 70s, his idea was, let's bring mathematicians and computers to build computational science can verify the safety of things around us. By the way, interesting part is 70s. Computers barely had any computational power, and mathematicians had no interest to get into that field. He was successful to do this. And Oden Institute is one of the main contributors where you have an airplane, you have a building you built, you can walk into this without any experimentation. You know it's safe. The reason for that is the computational models are supporting it. And the reason that this has been successful is you can always start with a simpler airplane, with a one-story building, and build up on top of it. You can always have sensors all over the place. And you can also have precise physical models that are hierarchical, composable. The problem with human is we can't have a simple human. Human is complex. And then a lot of abstraction models that we have at the level of cell, tissues, and so on, they are not well defined, so you can't really build them together. But this is really, that doesn't mean we should not tackle this problem. This was the figure that I wanted to show you all. Really, this is where we are today. I think, you look at risk factors. If I happen to have a glass of wine tonight, this is going to be the risk of you developing heart failure. Somebody tells me if you pass this street, there is a chance that you're going to die. And you can give me that probability, but I cross that street 100 times and I'm not going to die. That is not really the probabilistic risk factor that I want. What we need is really what NASA does, really precise trajectories and testing different intervention paradigms. So I don't want to take you guys. I'm going to skip this part. I'm happy to share papers. This was some of the work that Khan is the inventor. He is here. He has been using the notion of Taylor approximation in conjunction with neural net to build the physics-informed neural net for blood pressure. And the work actually, it works really well. He can build some of those physical models, and he can use it for AI. He has been looking at different kind of sensors, electronic tattoos, rings, and then normal wearables. So I'm going to skip that in the interest of time. And then I would just get to the end slide, which is really, I think, in this discipline, model-driven, physics-based AI is going to drive the next generation of advances. And we need really the personalization and the concept of digital twin. We need abstraction, composability, and hierarchical design. This is an example that I often use. The first Wright brothers flight was 12 seconds. 12 seconds is not a useful flight. But that was not the purpose. The purpose was to understand the fundamentals of flying. The fact that we can now go from Houston to Doha 16, 17 hours safely. The fact that we can travel at the speed of 5 Mach, but the fact that we cannot take that plane to the moon. So that's really, I applaud what you all do in academia, all of us. And then with that, I'm going to say thank you to our collaborators, our funding agencies. Some of my wonderful team members are here. And then I'm going to end with this quote from Dr. Feynman. Thank you.
Yeah, how about we take one question? And Roozbeh will be around so that we can go for the coffee break.
How about we take an easy question?
To enable more citizen science, I mean, it seems like you need more data to build these models. Are there any consumer-grade electronics that can that collect good enough data for contributing to any projects?
Are you talking about our efforts and in general what I see in the community?
Mm-hmm.
The latter?
Yeah, I mean, I assume you need more data from more people to essentially build these models.
Yeah. Thank you for that question. And your name, please?
Greg.
Nice to meet you, Greg. So yes, this is a really interesting question that you raised. If the AI development is tied to novel sensors of the kind that we are building, I really think that we need to have an integrated testbed where researchers who build the sensors, who build AI algorithms, who really understand the human physiology can work together. And that's something that I've been really trying to champion over the years. So from that perspective, we need to collect the data. But then the other aspect of it, as it relates to this, is that this is really medicine in the wild. I mean, the data is all around us. And I run a lot of studies at a large scale. We have run studies at 10,000 participants, for example. There is no way I can control the quality of the data the way I can control it in my lab. The other important aspect of it is if you happen to have a data that is coming to you from all these sources, how do you take it with a grain of salt? Again, build physics models around it that can reinforce the fundamentals, and then use those data points to train what you need to train. I'll give you one example. Many of us might have this Oura ring that gives us some information about our sleep, and during the day, it asks me questions like, how was the sleep, or did you exercise? I can answer that question correctly. I may not answer that question correctly. I have to take that label with a grain of salt. So sometimes it's even okay to take that data and start questioning everything, but then we start building the models that we need to build. There is also another initiative by NIH called Bridge to AI that they're really trying to bring all this data to the common platform, make the data AI ready, shovel ready, do the harmonization and so on. So there are also some certain directions in that domain. So,
Thank you.
Okay, let's thank again to Roozbeh.